Hello, students. This is the tutorial. This is tutorial number 4 for the course. So we cannot do it in the classroom. So I'm making this video for you so that you can watch it on your own. Um, Today I will talk about several problems that are designed to help you uh, consolidate your understanding about um, database indexes. So this is about the material that was covered in the previous week. So now let's look at the first problem here. We've got a relation. As you can see, the relation has three attributes, A, B, and C. Okay. And the question says the relation has six tuples. And these six tuples, they are stored in three disk blocks. Okay, so as you can see, this is the first disk block, the second disk block, the third. So I want to take the chance to remind you that every relation is stored as a file um, in the system. So this file has a logical order. So as you can see, the blocks are chained up according to the logical order. Okay, so this is the first block, and this is the second block. And from the first block to the second block, there is a pointer. Okay, and same thing here. Okay, very nice. So if you look inside the blocks, and then you see the tuples. So for example, if we talk about this tuple here, let me tell you how you should read it. This is the A value, this is the B value, and the C value. Okay, and what is T6? T6 is the tuple ID. I want you to remember that the tuple ID is not assigned by you. This is something that the system assigns automatically when the tuple is inserted. All right, now let's look at the three questions. The first question says you need to draw a dense B plus tree index on this relation for this relation. And this index is on a sequence of attributes, not just one attribute, a sequence of attributes. And this is A, B. And your index, your B plus tree needs to be parameterized by b small b equal to 3. So this says every node can store up to 3 elements. Okay, now talk about let's talk about this question first, okay, before we go to other questions. So as I always say, um, whenever you have a B tree or B plus tree in mind, you always ask the question, what is the total order? Okay, sorry about that. So what is the total order that the B tree is created on? Okay. When you have um, a sequence of attributes, A, B, and then there's a total order, the total order would have to be the lexicographic lexicographic order on AP. Okay. So for relation, this essentially says that you want to compare two tuples on attribute A first, and if their values are different on A, and then the comparison is immediately resolved. And if the two tuples have the same A value, and then you proceed to their B values to compare their B values. And if their B values are different, once again, the comparison result the comparison is resolved. And what happens? What happens if these two tuples have the same a value and also the same b value? So in this case, you will have to compare their tuple IDs. And remember, their tuple IDs are always different, and so you can always resolve the comparison using the tuple ID. So the tuple ID serves as the last resort. Okay. So let's take a moment to sort the tuples of the relation um, based on this lexicographic order. Okay. So as you can see, let's observe these tuples, right? Look at their a values. Most of them have a value 25. Actually, 5 out of 6 tuples have a value 25, and the a value of T3 is 30. So you know that T3 is going to be placed at the end, and let's do it here, T3. What about the other 5 tuples? Well, you have to compare their b values, right? Let's see. Well, their b values, interestingly, they're all 30. All right, so you can see that that the comparison results, the comparisons have not been resolved. Okay. So what do? Well, as I said, in this case, you will have to break ties using tuple IDs. Okay, so you put the ID with the, you want to put this tuple with the smallest ID first, followed by the tuple with the next smallest ID, and so on and so forth. Okay, so this is the lexicographic order you create over the tuples. Very nice. And now you can draw the leaf nodes of this B plus 3 index. Why? Because you know that the leaf entries are always sorted according to this lexicographic order that we just talked about. Okay, so let's do exactly that. So you want to have the leaf entry for T1. By the way, this is a dense index. As you can see here, it's a dense index. So you know every tuple should have a leaf entry in the tree. Okay, so let's first create a leaf entry for T1, and you need to store the A, B values of this tuple. Sorry, A, B value, so that's 25, 30. Okay. And also you have to store the tuple ID. Okay. And here there's something important. Inside the leaf entry, you also need to store the block, the address of the block where this tuple can be found. And so this is 38, and this is the address of this block here. As you can see, T1 lives in this block. Okay. So I want you to remember that the purpose of indexing is to locate tuples eventually. So that's the ultimate purpose. Okay, so you don't create an index just for fun. All right, you create the index for a very important purpose, and the purpose is to locate tuples. So if you um, have that mindset, and then it should be fairly obvious. You need to have something like this so that you can go from the leaf entry to the leaf node. Sorry, to the block in the file of the relation. Okay. All right. So that is the first leaf entry. That's the leaf entry corresponding to T1. So we'll move on to create the leaf entry for T2. So once again, um, I'm going to produce a leaf entry vertically. So once again, this is A and B, same as T1. This is T2. Remember, you also have to put the address of T2 here, and the address is 19 in this case. Okay, good. So I want to remind you that the maximum capacity is 3, right? So this b, small b here. So this means every leaf node should have at least 3 by 2 entries, right? So this means at least 2. So if you want, you can group these 2 entries into one leaf node, and that is perfectly fine. Alternatively, you can also have one more leaf entry inside, and that's what I'm doing here. So you can create another leaf entry for T4. Okay, so this T4 lives in block 23. So I have three entries here, and now I'm going to make it a leaf node. So let's have a green box here. Okay, so this is a leaf node. Okay, so this is the first leaf node in the tree. Okay, you cannot have another leaf entry into the node because that would exceed the maximum capacity. Okay, good. All right. So with the same idea, we're able to create the second leaf node. So this T5 lives in 30A. Okay, and then we've got T6 here, which is T6. Right, T6 is here, T6 and 19. And finally, we've got 32 for T3, which lives in block 23. Okay, so here you have 3 more entries. Okay, so this is another leaf now. Let's have a green box here. Because this is a B plus tree, you would like to link them up like this. Okay. Good. All right. So, so let's, I think it will be a better idea to really show just the boundary of the entries. So to emphasize, you should, the way that you should read the leaf entries is to go vertical. Okay, now we still have to create the internal levels. In this case, there's only one internal level, which is just the root. And there were 2 varying elements there. Now here you simply follow the definition of a B tree or B plus tree. You have to put the smallest element of each leaf. So this is going to be one child of the root. So you want to put the smallest element here. But you got to remember here, this lexicographic order essentially takes 3 values, A and B, obviously. But since we're talking about a lexicographic order, so you do need this T1, this tuple ID, for the purpose of time working, and therefore you want to have 25, 30, and then T1 here. So this is the smallest data element in the leaf. Okay. Okay. And then you also store the pointer to it, a pointer to the leaf. Now, you also want to create another leaf entry. Sorry, another routing element for the other leaf. Okay. So you are bringing the smallest leaf entry um, into the root. Okay. So that's it. Okay. So this is the tree that you would like to create. Okay. So I think that should be quite easy, right? That should be quite easy. So let's look at the second question. The second question here says, okay, is this a cluster index or a non-cluster index? Okay. Well, to answer this question, so all you have to do is to check one thing. Okay. So you can see, first of all, before we check that thing, let me remind you once again that the data elements of your B tree, they are always sorted. Okay, they're always sorted according to the lexicographic order that you define. Okay, so to answer this question, you want to look at the file. You want to ask yourself, is this file also sorted in the same way? Okay, so if the file is sorted in the same way. And then as we read the file, according to the logical order, we should see that the tuples inside are already um, placed in this lexicographic order we want here. Okay, but clearly this is not the case. As you can see, things are really messed up here. You know, this T3. How can T3 be placed before T4, etc., etc. So clearly this is not the same order, right? Therefore, we say this is a non-cluster index. Okay. Now let's look at question C. So this question C gives you a very realistic query. So this is A equal to 25. We want to find all the tuples satisfying this A equal to 25. So as a human being, of course, you know which are the tuples to be output, right? So you should output T6, T2, not T3 though, T4, T5, and T. Yeah. So what is interesting here is that, you know, you don't really have an index on A. Okay, so the index is created on AB, right? So this raises the question, is it possible to use this index to answer the query? Well, the answer is yes. Okay, the answer is yes. So in general, if you have a B tree created um, on a sequence of attributes, it may be possible to use the B tree to answer queries that are um, on a subset of these attributes. Okay, so this is one of those scenarios. Okay, we will see some more examples later, but if you have attended my lecture or watched my video, and then you know, in this case, the B tree is useful because if you look at the condition A25, it satisfies two conditions, right? The first condition says, you know, this is a prefix. Okay, so this A, so that is indeed a prefix of this sequence of attributes in the lexicographic order. Okay, so it's a prefix. Okay. I said two conditions, but the second condition actually does not apply when you have just a single attribute. All right, so this is something we're going to talk about later. All right, so I will find other examples to talk to you about these two conditions. Okay. Um, well, even if you want to understand this from another perspective, you can. Okay, so the idea is to look at the data elements and ask yourself, do you actually have a lexicographic order on A? Okay, so this is another perspective. Okay, so if you look at the data elements, yes, indeed, you can see that the tuples are sorted by A, and whenever you have ties, for example, these two leaf entries, you can break the tie using tuple ID, right? So as you can see, the ordering is quite consistent. Okay, so you can as well say that, you know, the B tree is created simultaneously on the lexicographic order on A. Okay, so this is the main reason why the B tree or the B plus tree is useful for this query. Okay. All right, now let's answer this query. Okay. Well, so in order to perform search, you want to convert this query, which looks like a point query. Right? It's like a point query because, as you can see, this is a point query condition. But you want to convert this query into a range query on the lexicographic order that the B tree is explicitly created on. Okay, so the lexicographic order is AB here, right? So you would like to convert the query into a range query, in this form, right? X, Y. And this range query would have to be on the lexicographic order on AB. Okay. And therefore, you will need to design this X and you will need to design this Y. And you know that this X will have to be something that you can place into this lexicographic order. So this implies that this X will contain A value, B value, and also a tuple ID. Okay, so it will have to be something that can be compared to the other data elements in the B tree. We talked about this before. There's one clever trick. You can achieve the purpose by designing this X to be something like this. The A value is 25, B value is minus infinity. And of course, you also need a tuple ID here. You can just place, minus infinity here. So this will be the X tuple. Okay. And then for the Y tuple, you will do something symmetric, this 25 positive infinity, and also the tuple ID will be something else, let's say positive infinity. And then you get Y. Okay. So now you can take a moment to verify that we have an if and only if condition. Okay. So you can see, for example, right? So let's say this tuple should be reported, right? And this tuple indeed falls into this range. As you can see, this tuple is larger than X in the lexicographic order and smaller than Y in the lexicographic order. Okay. Same goes for all these 5 tuples. And if you look at this one, it should not be reported. And you can see that this is greater than Y, and therefore it falls outside the range. Okay. Now, everything boils down to using this B plus tree to answer this range query. And you have to bear in mind that this is a non-cluster index, and therefore you would like to adopt a range query algorithm for non-cluster indexes. Okay, so the way to go is this: you want to find first the successor of this X. Okay, so if you do the successor, this is something we've talked about several times. So I'll just go quickly here. You start from the root, and then you go, you branch left. Okay, branch left. All right. Why do you branch left? Because you know that this is the predecessor inside the node. Okay, so that's why you branch left, and then you reach this node, and inside this node, once again you find the predecessor of this X, and which is here. Okay, so this is how you find the did I say predecessor? So I was wrong about that. So you are looking for a successor. So what you want to do is you want to again follow this branch, but here you identify the successor of X, okay, which is here. Okay. So this is how you find the successor, and then you can stay at the leaf level because the leaf entries are sorted, right? You can stay at the leaf level, and then you read from left to right. Okay. So let me identify um, the nodes that you have to access. You obviously have to access that, and also these 2 leaf nodes. Okay. Yeah, essentially you have to access everything in this simple example. But keep in mind that here we want star. We want star, right? We don't really have the B and C values inside the index, and therefore you have to go to the file. So from here you can see there are 5 tuples satisfying the query. Inside the index, you can already see this, all right, because you see their A value. Inside the index, you also have the B value, but you don't have the C value, right? So you still have to go to the file. But what I was saying is that from the index, you can already know how many tuples satisfy the query and what are their IDs, right? So it's T1, T2, T4, T5, T6. That should be fairly clear. Now, another thing that is fairly clear is that, look, you can collect all the distinct addresses that you have to access, right? So it's like 30A, and then you get another 30A here, If you want, you can do one access to 30A so that you can get T1 and T5 together. Um, so um, you so that's what you do. So you perform one IO read, one IO access to this block 30A, and that's how you get this tuple and this tuple. In particular, just their C values are what you're looking for. Okay. Likewise, you can see you will also need to do 19, and you can just do one access to the block with address 19. All right, so then you get T2 and T6. And finally, you also do an access to 23. So how many IOs are performed in total? You will have to perform 6 IOs. Okay, 3 from the index and also the 3 blocks in the file. Okay. All right, so that is problem 1. Okay. Now, let's go on to talk about the next problem. Next problem is extremely similar, okay? Except that this time the file is sorted differently. Now let's look at the file this time. As you can see, the file has been sorted lexicographically with respect to AB, okay? Look, as you can see, T1 goes first, followed by T2, and then T4, etc., right? So the ordering in the file is exactly the same as the ordering that we should have in this lexicographic one. Okay. So let's create the B plus tree, and the B plus tree is essentially the same, except that, of course, here, these addresses are different. Now let's give them the right address. This is 19 now, and T2 is that's 19, 23, 23, and 38, 38. Okay. All right, good. So this is the new B tree, B plus tree. Now the second question asks, is this a cluster index or a non-cluster index? And clearly this is a cluster index. Okay, so in general, if the data elements are sorted in the same way as the tuples in the file, and then you are looking at a cluster index. Okay, so as you can see, this is a cluster index. All right, now let's look at question C. All right, so question C, if you still remember, says now try to use this index to answer this query. Right? Select star from where, and then n equal to 25. Okay. The query algorithm is different from before because now the index is a cluster index. Okay. So when the index is cluster index, the algorithm will be faster. And now let me show you how. So as before, you want to identify the successor of this X. I forgot to mention. Once again, you want to convert everything into a range query by constructing this X and Y. So this X, as before, this can be 25 and then minus infinity, and then with the tuple ID minus infinity. Okay, so this Y will be 25, positive infinity, and ID positive infinity. Okay. So what you want to do is you want to once again identify the successor data element, which is here. All right. But the thing is, since this is a cluster index, you don't really need to scan the other data elements, scan any other data elements at the leaf level. So what you can do is to follow this pointer directly to the block containing this tuple. Okay. So basically, you don't have to access this leaf node. Okay. So why can you do this? What allows you to do this is that these tuples, they are sorted lexicographically on AB, right? So you can see that instead of scanning things here, you might as well just scan things here and then you will be able to collect the tuples basically in the same order. Okay, so this is exactly what we do. We go from here to this block, and then we start scanning, knowing that all the tuples satisfy the query, which means a value 25 will have to be placed together consecutively in the logical order of the file. So by reading um, by reading up to here, you'll be able to find um, all the 5 tuples that you should output. Okay. So what is the I/O cost then? So the I/O cost involves here these 2 nodes, these 2 nodes in the tree, and also these 3 blocks um, in the file. Okay, so the I/O cost will be 5. All right, so it's less than the I/O cost of the in the previous problem. Okay. All right. So I hope got some, you have learned some, you have got some pretty good ideas about how to solve these problems, in general. Okay, now let's look at this one. Here, this is the place where I want to talk about um, how to use or whether or not a B tree created on multiple attributes uh, can be used to handle particular queries. And now let's first look at the question. Okay, so here it says we got a relation, with A, B, C, D, and here we've got an index, and this index is created on A, B, C. Okay, so now the question is the following. I can tell you immediately that none of these conditions can be supported by the B tree. And the real reason is that you will not be able to uh, convert each condition into a range query. Okay, so let me tell you the principle. Okay, the principle is, can you support the query, the condition, let's say it's convert. Can you convert a condition into a range query? Range query, like this. Okay, S1. Are you able to do this? Okay. So if you are able to do this, and then you can do it, otherwise, the B tree is not good for it. Okay. All right. So let's see. Here, I want you to prove that this is not always possible for A. And how do you prove this? How do you basically saying, you're not able to guarantee such kind of conversions on all the possible relations. Okay. So in this case, all you have to do is to provide a counterexample. So let me show you the counterexample right away, so that you know what I'm talking about. Okay, so you got this ABC here. Now let's say I have 3 tuples. These tuples are here. Okay. Now let's see, right? So you can see this is I owe you D, right? Okay, so let's say I got D here. D, it doesn't really matter. So something like this. Okay. Um, so now you can see here, these 4 tuples, they are sorted. Lexicographically, right? According to ABC. Okay. Um, so indeed, you can verify, they are sorted lexicographically with respect to ABC. And if you look at these tuples, you ask the question, which tuple satisfy this condition? And let's see, right? you're able to see, okay, this tuple satisfies the condition, but this tuple does not, right? Because this 30 is outside the B range, right? But this tuple, the next tuple satisfies condition. So this is something we call a gap, right? So you have a gap here, so that you cannot say that the tuples satisfying the condition, they form a continuous range, right? And this is hard evidence showing that you cannot convert the condition into a range query like this, right? Because if you could do the conversion, and then the tuples falling inside the range must all be reported, right? So this is an if and only if condition. But as you can see, this is not possible when you have a gap, right? Good. All right, so this is the reason why this condition A cannot be supported by the B tree. Of course, you can also verify this using this rule I presented in the lecture, right? So if you look at the rule, you can clearly see violation there, right? The violation says you can only have one equality condition, but here you've got two. You can only have one range conditions, but here you have two range conditions, right? So you got a range condition here, and then you have another range condition here. Okay, so and that is not allowed. All right, so you cannot have two range conditions. All right, so that's why this is not okay. Okay, so let's proceed. So let's come to condition B, and again, I want you to give me a counterexample showing that this condition cannot be supported by a B tree. So here I'm just showing you a counterexample here. Should not be too difficult for you to find something similar. Say 5, 5, then 10, 10, 20, 30, 40, 30, and this is, let's say 0, 0, 0. Okay. So once again, you can check, you can verify that these tuples are sorted classical graphically with respect to ABC. And also let's identify the tuples that satisfy the query, satisfy the condition. The first one satisfies the condition. The third one also satisfies the condition, but not the one in the middle. Okay, so you can see you have 40 here. Okay, and therefore this is a counterexample showing you, you cannot use a B tree to answer it. Okay. So once again, you can use the rule I provided in the lecture. So this time, indeed, you have only one range condition. But the thing is, my rule, the template, right? The template I presented in the lecture and the video. The rule says the range condition must be on the last attribute. Okay, but here this is not on the last attribute. Okay, so this is the reason why you cannot use the B tree to support it. Okay. Now let's look at example C. Let's do it here. Okay. So A, B, C, D. Let's look at a counterexample quickly. So say 1, 10, 30, 0, 1, 11, 30, 0, and 2, 10, 30, 0. Okay, clearly these tuples are in lexicographic order with respect to ABC. And these two tuples, they qualify the condition, but not this one. Okay. All right. So you can't use a B tree to support it. All right. And once again, you can use my rule to catch this. My rule says, well, here you don't have range conditions, right? So it's not the range condition that causes the violation. However, my rule says you look at the attributes, and the attributes would have to be a prefix of the sequence here. Okay. However, you don't really have a prefix, right? Because you have B and C, so it's like B and C here is something that goes in the middle, but you are missing A here. So since you are missing A, this is not a prefix, and this is a condition that violates the template I provided. So it's not something that can be supported by the B tree. Okay, good. So that's problem 3. Okay, I hope you got the ideas. Now let's look at this problem. Now this problem is another way to test you on the same knowledge, right? So this time I say, okay, I got a schema A, B, C, D, and I want you to uh, create an index to support all these conditions. Okay. So the question is, what should be the lexicographic order you specify for this index? Okay. All right. This is something that this problem is not trivial. All right. So something that really requires you to perfectly understand the template I provided, the theory behind it, um, all this prefix thing, and this range condition constraints. Um, in order to answer this question, you really have to digest everything. Okay. So let's look at the first condition. Okay. So if you want to support this condition, one thing for sure, you know that DC will have to be um, the first two attributes, in the lexicographic sequence, right? I should have said the sequence of attributes that you use to define the lexicographic order. This is really such a long sentence, okay? All right, so you really need D and C to be the first two vertices actually in this order, in this sequence, okay? And then if this is what you do, and then you can see there's no violation here because, um, DC is the prefix, and you do have just one range condition. This is a point condition, right? You have a range condition, and this range condition is on the last attribute of this sequence. Okay. All right, now let's move on to look at the second condition here. Um, as you can see, we got D and C, so this is okay. This is consistent with the prefix so far. But you also have A, right? So you definitely should put A here. If you did not put A here, let's say you got something like B, and this is not something that can be supported, all right? Because we really um, need you to have this prefix. Oh, some students might ask, hey, I don't really see the sequence DCA here, right? You see A, C, D, okay? Well, uh, you are right, but the thing is, this and condition is commutative, right? So you could swap the order, D, C, A, and it's essentially the same condition. Okay, so DCA should be the first three letters uh, in the um, 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 sequence of attributes you use to define the lexicographic order. Okay. Now, finally, you can put B here, and this will allow you to support the last condition. As you can see, D, C, A, right? And then you have just one range condition, so everything falls into the right place. As you can see, D, C, A, B, right? So indeed, you have a prefix, and B is on B we have a range condition, but then we have point conditions on all the other three attributes. Okay. All right. So that's nice. So now we know we should create an index of R with respect to the sequence of attributes DCAB. All right. So that's the answer to this question. Okay. All right. So finally, we come to this problem 5, and this problem 5 is a slightly complicated problem, and this problem is about query optimization. So it's about how you can use different indexes to answer the same query. Okay. All right, now let's see. Let's look at some stats. So here we've got this relation, with million tuples, and they are stored in 10,000 blocks, right? Each block with 100 tuples. By the way, this relation has two attributes, A, B. This relation is clustered on A, okay? So it means it's sorted on A, not on B, therefore. Okay. So what else? Here we've got a dense index on A, and we've got a dense index on B. Okay. And both indexes have 3 levels. Okay. And also, um, how many entries there are in each leaf node. And this number is the same for both indexes. So here we've got a 2-dimensional query. Okay. So this is the condition on A, and this is the condition on B. Okay. So you have some further statistics. So Ka tuples satisfy the first condition, which is on A, and Kb tuples satisfy the other condition. And then if you say how many tuples satisfy both, that's Kab. Okay. Good. Well, I'm going to talk about 3 different plans, and I will analyze the idle cost of each plan. Okay, 3 different plans for answering this query. But before I go there, you should know there's always a trivial plan for answering this query, which is to store the whole relation completely. This is performing a full scan on the whole relation, right? So you do 10,000 IOs in order to read all the tuples, and as you go, you can easily identify the tuples satisfying the condition, right? Okay. Now, here you don't really see this full scan plan because that's trivial, but let's look at these 3 plans separately. Okay. So if you look at the first plan, basically it says, you know what, you first find all the tuples satisfying this condition. Okay. In other words, when you look for tuples, you pretend that you didn't have the other condition. Okay. So when you use an index to find these tuples, you simply ignore the index B. Okay. So you don't really look at this index B. And then after you have already found these tuples, and then you check on the fly whether those tuples also satisfy the B condition. Okay. In other words, sort of like you focus on the first condition and you focus on the index TA in this plan. Okay. Just to give you a heads up, you can also focus on the condition on B and use only the index on B to answer this query. So this is going to be the second plan. And then the last plan says, okay, I'll try to use both indexes. Okay. All right, so let's see how things are done in each plan and whether they're idle costs. Okay. All right, now let's look at problem A. So in order to use this index on A, so what you do is you use this index to find all the tuples qualifying this A condition. So let me show you the index, and let's say this is the file. Okay, this is the file. So what you do, I hope by now you should have been very familiar with this range query algorithm. So you want to go down one path, right? And then directly to the first tuple in the file satisfying this A condition, right? And then you can scan through the file, right? Scan through the file until you have exhausted the entire query range, right? 100 and 200. So why can we do this? This is because we have this are clustered on A. So all the tuples are sorted by A. Okay. So how do we calculate the IO cost? I think this should be fairly clear to you now, right? Because you would do so you would do three IOs to descend the levels of this tree, and then you will jump over here because there is a pointer store here, right? So you jump over here, and then you simply scan through everything. How many tuples you have to scan KA, right? So you have to scan KA tuples here, and every block can store 100 tuples, right? And therefore, a reasonable estimate would be KA over 100 and then taking the ceiling. Okay. So that is the IO cost of this plan. When you are doing the scan here, you see the B values of the tuples of these KA tuples, and therefore you can collect those tuples that also satisfy the B condition and output those tuples. Okay. All right. So that is what's going on here. This is TA. Now let's look at TB. Okay. Now this is the second plan. So the TB says, um, again, I'm going to use only one index, but this time this is TB. Um, so something important is if you look at the tuples that satisfy the B condition is here, right? You can no longer assume that those tuples are placed together in the file because the file is not sorted on B, right? So instead, you should imagine something like this. All those tuples get spread across the file. They can be anywhere. And even worse, those tuples, you know how many tuples satisfy this condition, KB. I mean, those tuples could be in different blocks, right? In order to read those tuples, you have to bite the bullet, as I always say. You have to pay one IO for every block, right? So you do have to pay an expensive cost, okay? But the thing is, how can you find the addresses of those blocks containing these tuples? Well, this is the place where you utilize the fact that this is a dense index. So every tuple has a leaf entry here. You know, it's a dense index. Okay. So what you can do is to go down the B tree, and then you want to perform a range query inside the B tree. Okay. So you do the blue portion here. And as you can see, every qualifying tuple has a leaf entry, and their leaf entries will have to be in this blue portion. Okay, and then you go from the pointers that are stored inside these leaf entries. So this is essentially what you do. Okay. All right. Now, how do we calculate the IO cost? Well, so first of all, it's two for descending the internal levels. All right, you've got two levels there. So it's two plus what? Two plus, you have to look at how many leaf nodes we have to access here, right? So how many leaf nodes are there? In total, there are KB leaf entries you have to read, and every leaf node can contain 200 entries. Okay, so you take the ceiling here. So that will give you the number of leaf nodes. But let's not forget, right? You also have this KB at the end because you have to spend one IO per qualifying tuple. Okay, so that's the expression. By the way, you cannot really directly compare these two and say which one is larger, okay? Because it really depends on the values of KA and KB, right? Of course, if KA and KB are the same, and then plan one will be much, much faster. But it's also possible, this KB could be much smaller than Ka. So as you can see in practice, Query Optimizer is really, really doing a great job considering all different possibilities. Okay. So now let's get to the last plan, right? So the last plan tries to use both TA and TB to do the processing, okay, to do the processing. So for this purpose, what we're going to do is we will look at the leaf entries of the A index as well. Okay, so let's say the leaf entries of the A index is here. These are the leaf entries that fall into the range from 100 to 100. Okay, but in this case, you will not go to the files. Okay, you won't go to the files. Okay, let's clear this. Okay, you won't go to the file. So you will descend 2 levels there. Okay, so you do this, and then you are able to get the tuple IDs. Okay, now remember, every leaf entry contains the tuple ID of the corresponding tuple, right? And here you got tuple IDs here. So if a tuple satisfies both conditions, and then this tuple ID should appear here and also appear here, right? So you'll be able to find the common tuple IDs, right? So how do you do this precisely? You will have to load all these tuple IDs into the main memory, and also you're gonna do the same thing here. And then since you have all these IDs in the main memory, you can do whatever you want in the main memory to find the common intersection. So there's just some CPU time, and there's no IO cost there. Okay, but of course we have to assume these tuple IDs can fit into the main memory, and this is usually the case. Okay, because our memory is quite large these days. Okay. All right. So if that is the case, and then you will be able to identify hopefully a small number of tuple IDs that fall into the intersection. Let's just say that here will be 3 of them. Okay, and then you will follow their pointers, respective pointers, in order to retrieve the tuples. Okay, so once again, you cannot really assume that these 3 tuples, these KAB tuples, right? KAB. So I mean KAB. So this is the value here. Okay, you cannot really assume that these tuples are stored in consecutive blocks, right? You have to make the worst case assumption that these tuples could be anywhere on the disk. So how would you estimate the total IO cost? Well, if you do this part inside TA, it's 2 plus Ka over 200. Let me explain this for you. So Ka is the number of leaf entries you have to read. Every leaf contains 200 entries, right? So you take the ceiling there. And you also have to do the same thing for KB. Okay. And then you'll be able to get the tuple IDs. How many of them do you have? You have exactly KAB, right? So for each one of them, you have to perform an IO to get the corresponding tuple. Okay. So these will be reasonable estimates for the IO cost of these plants. Okay. All right. So thank you very much. I hope you have learned something from this tutorial. All right. Have a great weekend ahead. All right.